Hello everyone, I'm Roshan Saman. I'm a graduate student at the University of Kentucky. My advisors are Dr. Jesse Hogue and Dr. Michael Siegler. This presentation is about small satellite attitude control using piecewise sinusoidal controls in the presence of disturbance torques. Conventional rigid body attitude control systems involve the use of reaction wheels, momentum wheels, or control moment gyros. These actuation systems are not ideally suited for small-scale applications because they tend to be heavy, require significant power, and are subject to friction wear. Instead, we explore the use of attitude control systems that use internal oscillating mass actuators that exploit the non-commutative nature of rigid body orientation. Our satellite system consists of a rigid body B and three pairs of rotational mass actuators mounted along the three body-fixed orthogonal axes. The kinematics of the satellite system is given by R dot equal to R omega, and the dynamics is given by omega dot equal to this function f. Here R denotes the attitude of the satellite. R is an element of the special orthogonal group SO3. Omega is the angular velocity, and omega cross represents the skew symmetric form of omega, which is an element of small SO3 or the set of 3 by 3 real skew symmetric matrices. T is an external torque or moment. U is the control whose elements are the rotation angles of the actuator pairs relative to the body. This control is suitable for rotational mass actuators like servo motors, which accept rotation angles as inputs. For the case where the external torque or moment is zero and the initial angular velocity is zero, the dynamics simplify to omega equal to ku dot, where k is a matrix that depends on the moments of inertia. This case was considered in our ACC 2020 paper. One example of this case is a small satellite system on an air bearing with the center of mass and center of rotation co-located. Another example is a small satellite system in deep space. The focus of the current work is the case where non-zero external torques or moments are acting on the satellite system. One example of this case is a small satellite on an air bearing with offset between the center of mass and center of rotation, which will result in a moment due to gravity. Another example is a small satellite in low Earth orbit experiencing aerodynamic torque. Because of the non-commutative nature of rigid body rotations, small angle oscillations about two orthogonal axes will result in a net rotation about the third orthogonal axis. This idea forms the basis of the control design in this work. We first focus our attention on rotation kinematics and ignore the dynamics. We consider two different types of angular velocities in the kinematics. Let C be a real number, frequency omega sub 0 be greater than 0, and let S be a rotation matrix. First, we consider angular velocity with elements that are sinusoidal, but about the orthogonal axes Si hat and Sj hat, which are nothing but the axes I hat and j hat rotated by S. These two sinusoidal elements have amplitude C, frequency omega sub 0, and a mutual phase difference of 90 degrees. The element about the third orthogonal axis Sk hat is 0. Next, we consider the rotation R tilde caused by the non-sinusoidal angular velocity omega tilde about the axis S mu hat. It has a constant amplitude. Both the amplitude and the axis of omega tilde are functions of C and omega sub 0. This angular velocity results in a pure rotation R tilde about the axis S mu hat. Next, we compare the rotation due to these two different angular velocities. Consider a time interval Ts equal to 2 pi over omega sub 0 and let k be a non-negative integer. Then this important result shows that the rotation r due to a sinusoidal angular velocity equals the pure rotation r tilde at times kts, and the geodesic distance between r and r tilde is bounded at all times. Furthermore, if the frequency omega sub 0 is much bigger than c, then the distance between r and r tilde during the interval kts to k plus 1 ts is small. We consider a control U, which is updated at times KTS. Its elements are piecewise continuously differentiable sinusoids with frequency omega sub 0. Gamma k is the control parameter, which is updated at times KTS. We call this particular form of the control U the admissible control. Now, in the case where the external torque is 0, we have seen that the dynamics simplify to omega equal to ku dot. Then differentiating the admissible control yields a sinusoidal angular velocity over the update interval. Thus, we can use the key approximation lemma to analyze this control. Next, we revisit the control design of the admissible control for set point tracking from last year's ACC paper, which focused on the case of no external torque. Let RD be a desired attitude set point. The objective was to design an admissible control U such that R converges to RD. First, we sample R at times KTS to obtain RK, and the error Zk, which is then used to compute gamma k, which is the control parameter. Here, n is a positive integer and acts like a gain. Particularly smaller n results in large amplitude controls. Also, this algorithm has no angular velocity feedback. The main result is that for all initial conditions, the control achieves asymptotic set point tracking. Next, we consider a simulation example of a small satellite on an air bearing where the objective is to track a set point of 5-degree pitch angle using an admissible control. In this example, we use the control algorithm presented on the previous slide, which is the algorithm from the ACC 2020 paper. When the center of rotation and center of mass are co-located, that is when there is no moment due to gravity, the algorithm yields the desired set point tracking. However, when the center of rotation and center of mass are not co-located, that is when there is a moment due to gravity, the algorithm fails to achieve set point tracking. To address set point tracking with an admissible control in presence of external torques, we modify the previous algorithm to use angular velocity feedback along with the attitude feedback. At time KTS, we use the angular velocity data over the interval k-1ts to kts to compute the mean angular velocity omega mk. Then we use the attitude feedback at the current time step Rk along with this computed omega mk to compute R hat k ts, which is an estimate of the satellite's attitude at the next time step due to the external torque, assuming that no control was applied over the interval kts to k+1ts. We call this the one-step ahead prediction. The estimate R hat KTS is then used to calculate the admissible control at the current time step KTS. Note that if there is no external torque, that then omega mk, which is the mean angular velocity, is 0, and the estimate R hat KTS is the same as the current attitude Rk, in which case this algorithm simplifies to the 1 in the last year's ACC paper. Next, we revisit the set point tracking example for a small satellite on an air bearing. The offset between the center of mass and center of rotation results in a non-zero moment due to gravity. We use the admissible control design with the modified algorithm for set point tracking of 5-degree pitch. We use the same control frequency omega naught as the previous example. We see that the new algorithm yields superior set point tracking performance at 2 different values of n, particularly n equal to 1 and n equal to 2. Next, we consider an example of a small satellite in low Earth orbit, which is experiencing an aerodynamic moment. The objective is to track a set point of 20-degree roll, 40-degree pitch, and 20-degree yaw. We see that when with the modified algorithm, the satellite is able to track the set point. For this example, we also observed the set point tracking performance of the 2 algorithms over 24 hours. We observed that at the end of 24 hours, the algorithm in last year's ACC paper resulted in an error of 7.45 degrees, while the modified algorithm resulted in an error of 1.32 degrees, which shows an 82% improvement in set point tracking. The extension and future work involves stability and performance analysis in the presence of external torques, which is missing in the current work. The other thing is extension to control design to address strict actuator stroke constraint, and examining potential benefit of using multi-step ahead predictor instead of a one-step ahead predictor that we use in the current algorithm. Finally, we'd like to thank the National Aeronautics and Space Administration and the National Science Foundation for supporting this research. Thank you.